All right. So if you remember, we finished our version of Kislitsin algorithm last time, finding smallest and second smallest. But at the end of the class, there were lots of suggestions from Param and Renan and Bert, who is no longer with us. Maybe it is Bert who is, no, it's not Bert. So about instead of keeping two lists, to keeping one queue. And I think I want to spend just before we are done, I want to spend a little time revisiting our algorithm, because their suggestion was oh so very good and led to so many beautiful things. So first of all, let us take a look at the main algorithm again. And as a result of all these suggestions, all the other algorithms sort of disappeared. Right now, we could keep only one version because it's so beautiful and so wonderful that we don't need others. So let us quickly, for those of you who forgot, compare dereference is this little thing which allows you to compare two things while dereferencing further. You do not compare values. You're given two iterators, two pointers, and you go further and compare values to which these guys point. It's very handy for us. But that's our main algorithm. First, there is all kind of machinery for creating function object, but the code is really very, very simple now and straightforward. So for every element in our binary counter, we'll come to binary counter in a second, we keep a value of the iterator which actually sort of won the games. And we keep a queue of people who lost to these guys. So this argument type is an iterator type which points to the value which won. And then we have a pair where the first element points to the beginning of the queue and second element of the pair points to the end of the queue. And I mean the real part of the queue. I don't mean past the end. Right? So what do we do then? We say that if the second guy, if not if y, I'm lost, guys. I cannot read my own code. If y loses, no, it's not what it says. If y loses, thank you very much. If y loses, then we know that we would no longer need the list of people who lost to y. Y is out of competition. And we need to add to the list of first guy x that second, the iterator of the y guy. Right? On the end, on the back. Why on the back? Because he comes from that order, from over there. Otherwise, we do the same for x, but we add to front. So that is the fundamental difference. It's a very, very simple thing. Yes? Those of you who have some memory of what we were doing, it used to be a very huge and incomprehensible function. Let us look at the main algorithm now. So the main algorithm now says that, well, first of all, if first equal last, if there's no elements, or if there's only one element, just return pair first last. It's a trivial thing. So we know that there is at least two elements, which also tells us that the first round of the competition will have at least one game, and then the winner will have at least one loser on his list. That's the nature of tournaments with two people. Then we do very few things. If it's your broker, you have to answer. And you probably want to sell. Okay. So couple of type defs. We say that we create this op type thing. This is exactly the function. This is exactly the function object which we looked at. All right? Constructed out of our compare. And the second thing we need in Iterator, we will see why. And you say, how come your list pool has iterators? Or just take it on faith for a little while. We'll get to iterators. For the first time today, we will see iterators. Then we create a list pool by just saying that give us a list pool. And we do reserve 256. This, of course, we do not need this line. But 256 would allow us to run up to whatever, 100,000 or so without reallocation. So actually, list pool is quite small. We don't remember, this is just a square of log. You remember that, right? So we create a list pool. Then we create this compared to reference object. Then, which doesn't do anything. So this stuff doesn't do anything. They're actually not a single instruction literally generated by this line. So it's just setting up the stuff. Then we create a binary counter. And our 0 is last. Remember, our identity, our counter needs identity element. And our identity element is last. And pool empty queue. We will see what it is. It's basically a pair of two nils in the pool. So, and then actual algorithm, if Ryan would be kind enough to show it to us, could have been done in 4 lines, but people suggested that it's clearer if I introduce 2 temporary variables. Actually, could be done in 3 very long lines. So the first thing, we keep feeding things into the binary counter one by one. So we sort of make pair first, and with the same empty queue as it is, and throw it into the counter. And it will be immortalized. Thousands and thousands of people are going to. Okay, so we fill the counter, then we reduce the counter and get the argument type. What's the argument type of the counter? It's a pair where first element is the iterator and the second is this queue, another pair of pool iterator-like objects. They're not iterators, actually. So we got this. So we know what is the smallest element. It is just whatever the result of this was first. And then here we're again doing something which we couldn't do before, but right now we can, because somehow we obtained these iterators. See, up there we type def and iterator, which magically appears. what we could do, we just run standard min element algorithm on iterator from the pool min list second first, in the iterator pool, which is nil, with compared to reference. Right? So we just use a standard algorithm. So again, believe it or not, all this complicated algorithm is done in fundamentally these two lines, while and then reduce. The rest is sort of pretty trivial. Now, so what I need to show you, first of all, I need to show you what we could do now with you guys' insights with the list pool. So if our friend will show us list pool. So the beginning of list pool is pretty much the same, except just 1 second, for some, to make it, we did have list type, but I added the thing called value type, which is a standard sort of name for T. We will use it, you will see one later. But the interesting stuff is at the end. It's very trivial, very elegant, and allowed us to write this code. So when this is just Lisp-like interface for the pool. Till we come to the end, stop. Get to operations on queue. So first of all, we define a type def. We say there is a pair type. The pair of nodes is a queue. Now, pair type is empty if isAnd is first. If we have nil there, it's not really a queue, it's an empty queue. All right? Then we could create empty queue by doing pair type of end. All right? We used it, by the way, in the. So now we have two elegant little functions. Pop front, we don't need pop front now. Could you show us two pushes? We defined pop front. There is obviously no pop back, singly linked lists. I cannot pop back fast, and I'm not going to provide you with a linear time function which pretends to pop the end. If you want to do it, write it yourself. All these functions are constant times, they're very fast. So let us see what push front does. It always allocates a node. So it starts allocating a node from value to p first to the beginning of the queue. And then it says, if the queue was empty, then return new node, new node. A queue with one element, the same node is in the beginning and at the end. Should be self-evident. And otherwise, return pair new node and whatever was the last node. And then push back, basically identical. We allocate. In both cases, we need to allocate. But remember, our allocate, it's literally two instructions. It's, these are no allocations involved in the sense of malloc. So we do allocate. We do compare again if it's empty. If it's empty, we return new node, new node. Otherwise, we have to set the end of the old last node to the new allocated node. We have to do replugzy for those who remember Lisp, such as Hernan. So we do replugzy to new node and return pair p first new node. New node is now the last. It's the same. So, and again, we have a very efficient free, unlike our earlier tries, where we tried to imitate Lisp. Now we could free a long list with constant time, in constant time. by basically saying free pair, where what we do, we just take this list, since we have nodes both to the first node and the last node, we literally just attach it. We do replug of the end of this guy to the free list and replace free list with the beginning of this guy. So it's a very, very fast thing. Sort of, again, what it shows that, for me, there were just many wonderful lessons. First of all, it's good to work with other people. I have been working on this algorithm I've been teaching it clearly for about 30 years. And so, do I know it? Yes. But, I work with you guys, and now I have a much more elegant version. It's not much more efficient than my old version, but it's also much more elegant. And I'm actually eternally grateful to the guys who pushed me into that. But there is not just this algorithm. It's a much more important thing which we discovered. We discovered that list pool, which is a very, very useful thing, could function in a slightly different, again, the intent was to provide Lisp-like thing. Lisp doesn't make you think in terms of singly linked lists where you keep a pointer to the beginning and to the end of the list. It's not an idiomatic thing, so I didn't do it. But then, again, you showed me that by adding few little functions, we could change the code and becomes so much better. Thank you for that. Now, so we learned that, but there are some mysteries. And the mysteries is that I introduced an iterator. And why did I introduce? Now let me talk a little bit ahead, show where I want to go. We introduced this wonderful thing that, let's look at it very quickly before, called binary counter. Just a reminder what it is. We introduced this binary counter, this thing which sort of basically allows us to take any associative operation and do parallel reduction without recursion, iteratively, and with using only logarithmic space. Some people, hypothetical people, may be misguided. They might think that it's just useful for this algorithm. It's useful for many, many different algorithms. It's one of the most powerful algorithmic structures I know. Right? Because there are very many divide and conquer algorithms, and it handles them all just so beautifully. So what I want to do now, and I think it's a very instructive path, is to see how we could implement linked list sorting. Right? It's a different algorithm, no relation to what we were doing. But I claim that the same binary counter will just magically do it for us, and do it much more efficiently than most implementations you will find. First. Second of all, to do it properly, we'll have to deal with things which we need to do anyways. Because to do list merge, list sort, we need to do list merge. To do list merge, we need to learn about iterators. Why do we need to learn about iterators? Because the only linked list we want to use are lists out of our list pool. And if you remember, we didn't provide them with iterators because we were lazy. We said, we'll do it later. Now is the time to do it. And I think it's very important because it will allow us to learn to write iterators. Right? Once and for all, we will sort of learn. Remember when I joined A9, somebody, even one of the top people here, told me that I should learn to write iterators. So I'll prove now that I learned. I'll ask. So okay. And we'll use this spoon for iterator writing. So we will do it together. But before we write them, let me tell you a little bit about iterators. Again, many of you use them. Anybody who programs nowadays in C++ is forced to. Right? If you use vector iterator, whatever. But there's lots of people who do not quite understand what they are, and partially because iterators are called iterators. As Param told me once, he couldn't understand what they do till I told him the right name for them. You see, iterators, there is a thing in computer science called iterators, which first appeared long time ago in the mid-70s, around 75, 76 at MIT. It was invented by Barbara Liskov, who were designing a language called Clue. Yes. And she was influenced by another great and very successful language done at CMU called Alphard. So there was, yes. So there was a language, Alphard, which never existed. This is one of these things. It's a mythical language. It was never implemented, but many, many people got tenure because of it. So designed by people at CMU, which had some interesting idea, including the idea of a generator, where generator, for those of you who know Python, which is most of you, this is like iterator in Python. So Barbara Liskov said, oh, wouldn't it be nice to write for something and do like that? So she introduced the notion of an iterator, which was like generator in Alphard, which was a procedure which returns multiple values one by one. Right? It's a procedural abstraction, first. Second of all, you could have only one iterator, at least in Clue. You could have only one iterator to a data structure. And it was something which extends for statement, generalization, sort of a generalization of a control structure. Now, roughly at the same time or later, I was working on sort of my how to do algorithms, and I introduced the notion of position, or sort of a better name is coordinate, sort of the name which Paul and I use in our book. Sort of coordinate is some way of indicating where in the data structure you are. It's not a control structure. It's just a pointer into a data structure, generalized notion of a coordinate. And eventually I started talking to C++ guys and saying, so you see, you could do this and this. I said, all we know, said them, we call it iterator. Of course, they didn't call what I had an iterator. They had some C++ codes where they were trying to do Clue-like iterators, a heavy state procedural things, which sort of, instead of lightweight pointer-like things. But I chickened out. I said, oh yes, guys, that's what you have, what you call iterators. So I thought that it's much better to win with a wrong name than lose with the right name. So the name is stuck. It's in the standard. But again, the concept which it designates is not a concept of iterator in Clue or iterator in Python, which is or not iterator in Java. It is literally iterators, of which we are going to be talking, which we'll be using in algorithms. It's a generalization of a coordinate in a data structure. It's a lightweight thing. It doesn't do anything. It just points to something. Right? And there are these arguments which I hear, again, the Boost guys right now, like John Franz, they say, oh, iterators are all wrong. Let us go back and do ranges. Guess what? They're reinventing Barbara Liskov iterators. So, by the way, just for the record, when I introduced my iterators, I was very familiar with iterators in Clue. Moreover, I was even very familiar with Barbara herself and with Alan Snyder, who co-designed iterators there. So the reason I didn't do what they did, because I thought I wanted to do something else. So just for the record, it wasn't done out of ignorance. Maybe I was stupid, but I wasn't ignorant. So the idea of what I wanted to accomplish is to have something which allows me to navigate through the data structure in a natural way the data structure navigates. Again, I don't want to do it. There is this book of which you heard many times, and many of you have, Elements of Programming. If you look, there is a chapter on coordinate structures, which try to present a general view of all of that. And right now, what we will try to write is to write an iterators. John, would you like to help me?
Okay.
So we want to provide, quickly, let us go to our list pool. By the way, I have good news. Pizza is here. So let us take list pool. Do we have list pool? This is list pool. Min element list needs to be deleted, by the way. I forgot. We no longer need it. Thank you. Okay, so we want to write. Okay, let me make a first move to simplify John's thing. Say struct iterator. Yes, semicolon. Okay, so now let us see. John, what do you think should be in there?
Well, there's a number of type defs that Iterator standard has. Things like
Yes.
the value type and the difference type and the pointer type and the reference type. I don't know what they all are.
There are 5 of them.
Okay.
I'll just tell you.
Okay.
So first of all, he says that there is a number of type defs. That's, he's trying to tell you how we write it. But let's ignore C++. What are we talking about? Why do we need this type defs?
We want to know what the type will be returned if we dereference it.
We want to find there is a term. Want to know
The value type.
affiliated types.
Oh, yes, okay.
Right? Sort of, again, there is a view which people say, oh, everything is in a type. Types don't work like that on their own. Types come in clusters, connected families of types. So if you have a type in star, there is affiliated type int. Right? They're 2 types. I mean, they are related. Right? And it would be terribly nice if we could obtain int out of int star. Right? That is, that if somebody gives me a pointer type, I could find out what this pointer. By the way, C doesn't let us do it. Neither does C++. So we're talking about that we need to have type functions, which allow us to have a type and get a type. And what we're going to see is how we solve this problem. I want to distinguish, because the problem which we talk is not specific to C and C++. It appears in Java, even in Python, in spite of its duck typing. There's still a connection between this and that, right? Even if these are duck types. But so there is a notion of a type function. But what we implemented, as John correctly said, we implemented with a type def. And John said that the first most important type def for an iterator.
It's the value type. It's what you're going to get when you dereference it.
Yes. Remember, int star and int. So how do we do it?
Type def and then it's called value type. I'm not sure what we want for this one.
Let's be sure. Any sort of what's the value type of list in a list pool?
It's the list.
No.
It's a node.
No. It's element in the node. If we have a list of integers, what's the value type? Int. And by the way, let's go up for a second. We even have value type right there. That's why I put it so, to make it easy for you to write. Huh? So, but it requires something, so let's go and see how we write it.
Are we templated on list?
No, we're not templated on anything. We live inside list pool. Iterator to things. And I think no, you do not need to do type name. No, you don't. You just need to qualify. Okay, what you want to say, let's say it in English. I want to say that the value type of an iterator is the same value type as of list pool itself. Does it make sense? So how do we say it?
List pool value type.
Yeah. He's telling you. Or, look, I mean, telepathy is too much for me. You know. But, okay. Yes, very good. That's the most important one.
And then we want probably, I think there's a ref type.
Let us ignore, okay, let me tell you that there is a following way of viewing. There are 5 things altogether. 3 of them are primary, 2 of them are secondary. I'll explain why. So, the first thing is, of course, value type. Then there is a very important, any iterator type has an integral type affiliated with it. C guys discovered it a long time ago. I think Larry Rossler discovered it. And because he discovered that if you have pointers, you need to define something called pointer diff t. Right? Because you don't know. But for iterators, you couldn't just say pointer diff t, because the size, what's the length of a range expressed with iterators depends on the iterator. We call it difference type. So difference type is an integral type. This is a definition, guys. Integral type is difference type is an integral type large enough to encode any valid range of a given iterator. Right? It could be int 8, if iterator, whatever it is. So we know the name, so it's difference type. But what is it?
Well, pointer diff t would work.
First of all, we don't know that. Pointer diff t, we might work on a machine with 32-bit pointers, but with 64-bit integers. Silly machine, but you know, it's possible. Why you're not looking where you should be looking. Look at the list pool. Show him the beginning of list pool.
Oh, we have size t there.
No, we don't have size t is a default. N, which we actually called list type here, which tells us how long the link is. We could have a list of integers with 2-byte links. Or we could have, we typically make it size t, which is going nowadays. But it's not necessary if our lists are relatively small, as they are in our application, by the way. I didn't bother to optimize, but I could have quite safely make it something like u in 16. Would have been, since it's log square, it would have lasted for the. So we have it. So you understand.
So list type would work for us then.
List type will work for us because you couldn't have more nodes in the list than you have than you have nodes. So let us do that.
So you said there's 3 primary types.
3 primary types. And the third type, while it's primary, it's actually shouldn't be a type. But we have to make it a type because of limitations of the language. Again, we need to distinguish between how we type it in C++ and what's the notion behind. The notion behind here, of course, is that there are different categories of iterators. Right? What kind, for example?
So we have the iterator tags.
So we have forward iterators, bidirectional iterators, random access iterators, right? Or input iterators for those who know what they are, but they're different categories, different theories of iterators. Yes? But what we do, we use the tag type to designate the category because we do not have support for theories, for concepts in C++. We have to do it in this way. That is, every type could use tag types to denote which theory it supports. And then you could use this tag to do compile time dispatch. That allows us at compile time choose the correct algorithm. We will see all of that, but So the third thing is type def. No. Well, we haven't done the second. Yeah. Let us do the second. I need. Michael, could you order me an extra pair of eyes next time? So.
All right. So we want the category type. What's it called?
Yes, it's called iterator category.
Iterator category.
Right. So we know its name, and we know what is it. What kind of lists are these? Singly linked lists. So we need forward iterator. There's no way in a singly linked list to go back. It just cannot be done. Not even if you use inheritance. So I get all these angry messages for my remarks about inheritance from your friends.
And you thrive on it.
No, I'm devastated, as you could see. I don't sleep nights. I cry. Okay, so what was it? Is it going to be? Forward. So you say forward iterator tag, but where do you get it? So it's std. Forward. Very good. Very good. Tag. What is it called? Iterator category. Right? Again, type defs work backwards. Unlike defines. Whatever. That's how it is. How it is. So now, but I told you there are 5s. And here I have to tell you an amazing story because it would be just 3. Actually, there would be just 2 if there was support for concepts. Because the 2 natural things are just these 2. But when I was doing this stuff, there were all kind of companies opposing me. And there's this company you might have heard called Microsoft. And Microsoft said, we are going to vote against STL unless it accommodates multiple memory models. Remember, they had tiny pointers and huge pointers and long pointers. And they wanted it somehow to work with all of them. And, you know, I never, by the way, I sort of never knew what they were. I had to figure out what's the difference between the long pointer and huge pointer. Anybody knows? Yes, but in terms of operations, what's the difference? They're both 32-bit pointers. Both, same size, 32-bit. At that, we're talking ancient history. But with long pointer, if you add 1 to it, and the first low 2 bytes overflow, it rotates without propagation. Yeah. With a huge, it does propagate to the 16-bit. So whatever. So they demanded that, therefore I had to change the whole architecture to accommodate them. Guess how they voted? No. So, you know, now we're stuck for the next 100 years with stuff which I included to placate people. He couldn't have been placated. So normally, the question is, what does iterator return when you dereference it? What does it return? Actually, it doesn't return quite the value type.
The reference to the value.
It returns the reference type. We're in C. If you dereference a pointer, you actually get an L value, something you could write. It's totally legitimate to say star I equal 5. So it's an L value.
It's the ref type, not the value.
It's a ref type. So I, of course, originally assumed that when we dereference, we just get T ref. But I couldn't do it anymore because it could be T long ref or T huge ref or T tiny ref. So therefore, every iterator has to provide us with a type called reference.
Reference type. Ref type.
Reference. Just reference. That's what it's called. And what is it?
Well, it's going to be an L value reference to the value type.
Well, it's going to be value ampersand reference. Right? So we always have to write it. It's not, we're not observing. It's, you know, of course people say, well, we're going to have very clever iterators iterating through the disk and doing some other thing. Well, we'll replace references. But in reality, nobody does that. But you still have to write it, always. Reference, no type. And then there's one more type. See, if you have a reference, what else is there like a reference? Pointer. Because what if somebody says ampersand star I? What do you get? And of course, I was perfectly certain that he would get a pointer, normal pointer. But no, according to Microsoft, he cannot get a pointer. He will get a pointer. So let's write it. Value type star pointer. Yeah. It's not. This is not particularly harmful, but you know, this obfuscates things, and it's of course loved by language specialists because it provides them with steady employment. They have to go and teach people about all this stuff. So, okay, if we were designing language from scratch, we wouldn't have no type defs, we would have type functions. And if we would have type functions, we would have 2 type functions, not 5. Okay, very good. So let us ignore constructors for a while.
Okay. We need to be able to...
What do we need to do with a forward iterator?
We need to be able to dereference it And we need to be able to increment.
And how?
Equality compare.
And
Inequality.
yes. Yes. All of these are controversial things. Remember, it took me ages. I mean, they still argue. You know, I just had a message from one. Who is the head of Finnish delegation to the Standard Committee? He's a powerful guy. I forget. I have a message from him explaining to me that you guys are still fighting out whether less than is opposite, greater, or equal than. Right? I have maintained since the third grade, I think, that it is. But there is a large distinguished body which still apparently arguing. We will talk about it very, very quick. So let us start with, okay, maybe we cannot write the code without we decide what is inside. So who lives inside there? Could you think what the state of this iterator should be?
It's going to be a node.
Would it be enough? Let's think, guys. Let's think about it. What's our implementation? At some point, you have to forget all kind of theory and think about what's the implementation of the list pool. What is it? What is it? It's a vector, yes? So to find node in a vector, what do you need?
Just need the index then.
Indexes, very good. And what else do you need?
Well, you need to know the.
Yeah, you need a pointer to the vector. Beginning of the vector might not quite good. Why? It might reallocate. So, but a pointer to a vector or a pointer to the pool, which is identical, will just work. Do you agree?
Sounds like it.
So we need to have a pointer to the pool, and we need to have an index. What's the index type?
It would be the vectors.
Difference type, because it's the difference between 0 and int.
What? List type is that thing, yes. Is it? Let's go see. I forgot, guys. I forgot. I apologize. I have a mental block.
Node type.
No. Why? I'm just list. No. I'm looking at it, and I am not happy. I am not happy at all. I see. The problem was that I got stuck with the recursion. You see, I need to define this node to have list type, to define this vector. And I cannot get a difference type of the vector without I'm sort of stuck in the loop. So I think we have to just use, basically, okay, it's actually perfectly good, guys. We say, let's look at let me defend that, explain why could we go up, just a little up, just this. You see, do you take this type n? Type n tells you how many indices we could have. And what I'm saying that we cannot have vector, we don't need a vector, with length more than indices available in the pool for lists. Everybody follows? So if we make list pool where CUDAs, the next nodes, are just 16-bit. Our node space is limited by 2 to the 16. The size of the CUDA limits the node space. Everybody? Now, so you were right. It is list type. List type will just work. Could you? Yes. So list type, and what do we call it?
I think it's list pool, list type, right?
Yeah.
Pool index, or whatever we want to call it.
We could actually just say difference type, it will work. But I think list pool : list type is better because that will tell people the meaning. And I suggest the natural name for this thing is called node. Because it is iterator points to a node. And then before that, I think we need somebody before that.
The address of the list pool.
Something beeping. Dan got disconnected. Could you reconnect him, please? Why does he have to beep while being disconnected?
Skype.
Oh, he's on Skype. I'm not so sure. I'm less certain about privacy because you see, sometimes I want, I do some iterator algorithm, and then I want to get a node index out. It's a perfectly useful thing to get. So let us leave this, let us discuss it later. So let us not right away. People always jump and say, let's make it private. In my case, I'm a communist. Don't like private property. So I'm not really a communist, so don't call it that. I was accused of being a communist because that was part of me not being object-oriented. Seriously, there was a guy, I don't want to name his name, who wrote a long missive to the Standard Committee that STL was basically a communistic propaganda. And it clearly was a KGB implant to defeat. Yes. Objects are important, owning them and stuff like that. So he also owned a very large library vendor. So he didn't need to object because he then made millions and millions of dollars selling my code after running it through a pretty printer. By the way, that's a good way of making money. I'm not making it up. They sold it back to HP. I worked for HP Labs, but HP, of course, couldn't use the code from research because, researchers don't know anything. So they bought it from this guy for $1 million, who did one thing. He took my code, because the code was in the public domain, ran it through a pretty printer, which made it utterly unreadable, because pretty printer doesn't know anything about it. Not just templates, or for sure not anything about my code, right? So, and then sold it back to HP for exactly $1 million. That's free enterprise to you.
Did somebody investigate whether you get kickback?
I didn't get a kickback. I did not get a kickback. My total income from STL, I think, is somewhere close to $750. I got $250 for writing an article for Byte magazine, and I got $500 for invited keynote or whatever it was called at UPSLA. This is, and I paid taxes from both, by the way, for those, I don't cheat on my taxes. So, Okay, so, and the second thing we need to have the
The pointer to the list pool.
pointer to the list pool. So we say list pool star, and we call it either pool or P.
I'd call it pool because I would rather call it pool.
He wants to call it pool. Okay, let's call it pool. Okay, now let us see. How would you write an operator star?
Well, it's going to return our,
What does it return? Reference. It's always easy. After you've done this type defs, you just say reference, because that's what it returns. And then what do you say?
it's operator star.
Yes. How many arguments?
It doesn't take any.
Doesn't take any. And
It's const to the,
it's const. It's const to the iterator itself. Even if it's a non-const iterator. Because constness says whether you modify it doesn't modify the iterator. Of course, the guy, after you dereference, could write in there, but that's perfectly all right. It's const. Very good. The best and the brightest make this mistake. Okay, and then tell us what it is.
well, we want to return the node in that pool.
No, we don't want to return the node in that pool. I would say, I would start it with saying pool arrow. Because we obviously need to do something through the pool. Do you agree with that? And what kind of functions pool has? Do you remember? What are two main functions? Show us two main functions in the pool. Two main functions are value and next, otherwise known as car and CUDA. But we don't have to use idiotic names. So we call it value and next. So
we want the value
of
of node.
That's exactly right. Okay, now we go and eat pizza. You're not done. Far from it, but you're doing very well. Thank you.